A sensor is a device that detects and responds to some type of input from the physical environment. The output is generally a signal that is converted to human-readable display at the sensor location or transmitted electronically over a network for reading or further processing. Traditionally, lighting systems, air conditioning, and manufacturing have been operated with manual controls. In today's world, energy efficiency, water conservation, clean power, safety, and automation have gained importance in the engineering industry. To fulfill such demand and achieve peak efficiency in the industry, the addition and improvement of sensors has been essential. Because sensors can change a form of energy into another, they can be classified according to the type of energy transfer that they detect. Some examples of sensor classification are thermal, electromagnetic, mechanical, electromechanical, and chemical sensors. Thanks to technological progress, sensory accuracy, sensitivity, and applications have been improved. In this presentation, we will take a deeper look into some of the most widely used sensors out in the market. We begin with the photoresistor. The photoresistor is an analog device which converts light energy of various wavelengths, ranging from infrared to UV light, into electrical energy or an electrical signal. In the dark, a photoresistor can have a resistance as high as several megaohms, while in the light, a photoresistor can have a resistance as low as a few hundred ohms. When light on a photoresistor exceeds a certain frequency, photons absorbed by the semiconductor give bound electrons enough energy to jump into the conducting band. The resulting free electrons conduct electricity, thereby lowering resistance. The changes in resistance can be measured and used to drive other electronic components. For instance, you can use a photoresistor to turn on a light when a room gets dark. This principle is also used for street lights. Most portable personal electronics now have ambient light sensors used to adjust brightness. The most common use in our daily lives is in cell phones and tablets. Now I'm going to be talking about ultrasonic sensors. An ultrasonic sensor is an instrument that measures the distance to an object using ultrasonic sound waves. There's a wide range of ultrasonic sensors, and they vary in size, shape, and price based on accuracy needs. You may be familiar with the HCS-R04, which is commonly used for electronic projects. This one in particular offers range detection with high accuracy from 2 centimeters to 400 centimeters and has 4 pins. 1 is VCC, 2 is trig, 3 is echo, and 4 is ground. Ultrasonic sensors work by sending out a sound wave at a frequency above the range of human hearing. If there is an obstacle or object, it will bounce back to the sensor. By calculating the travel time and using the speed of sound, the distance of the object can be calculated. In this example, the time of flight is 2,610 microseconds. Dividing that by the speed of sound, we get a range of approximately 45 centimeters. Accuracy may be a challenge since the speed of sound varies with humidity, air pressure, and temperature. One way to overcome this inaccuracy is by adding a temperature and humidity sensor and factor that in with the speed of sound. Now I'm going to be talking about temperature sensors. A temperature sensor is an electronic device that measures the temperature of its environment and converts the input data into electronic data to record, monitor, or signal temperature changes. Temperature sensors are used in automobiles, medical devices, computers, cooking appliances, and other types of machinery. Some temperature sensors require direct contact with the physical object that is being monitored, while others indirectly measure the temperature of an object. There's a great number of different temperature sensors such as RTDs, thermocouples, thermistors, and semiconductors that are used for different applications based on temperature ranges, accuracy, and project needs. For example, RTDs offer high accuracy and temperature readings from -200 to 600 degrees Celsius. Thermocouples are specifically used when sensitivity is important or when a wide range of temperature readings is needed since it reads from -200 to 1750 degrees Celsius. A thermistor's effective range is -50 degrees Celsius to 250 degrees Celsius, and a semiconductor typically ranges from -70 to 150 degrees Celsius. In industrial applications, long cable runs between sensor and measurement system inputs expose them to electrical noise, wear and tear, and external voltage sources that can damage both sensors and their measuring systems. We can always add capacitors to create a low-pass filter to attenuate noise sources. However, these filters can extend settling time and can be problematic in approaches using pulses of excitation current. Now I'm going to be talking about passive infrared sensors. A passive infrared sensor, also known as a PIR sensor, is an electronic sensor that measures infrared light radiating from objects in its field of view. The term passive refers to the fact that PIR devices do not radiate energy for detection purposes. They work entirely by detecting infrared radiation, radiating heat, emitted by or reflected from objects. They consist of a specially designed cover called the Fresnel lens, which focuses infrared signals onto the pyroelectric sensors. When the sensor detects a moving object, the signal can be used to control other devices. PIR sensors are commonly used in security alarms and automatic lighting applications. This sensor has 3 pins. Number 1 is VCC, number 2 is out, which gives out a high logic level if an object is detected. Number 3 is ground. They also have 2 potentiometers. The first one controls sensitivity up to 7 meters, and the second one delay time, which is anywhere from 0.3 seconds to 5 minutes.
Hello, my name is Laura Goes, and I'm now presenting MQ gas sensors. MQ gas sensors are also known as chemiresistors, as the detection of gases is based on the change of resistance of the sensing material, in this case, tin dioxide. In clean air, electrons in tin dioxide are attracted to oxygen atoms absorbed on the surface of the sensing element. When harmful gases are being detected, the oxygen absorption rate decreases, allowing current to flow through the sensor. This current triggers an increase in the resistance of the tin dioxide, generating a voltage value. From this image, we can observe the outer part of our sensor. This is called the anti-explosion network. The anti-explosion network is made of stainless steel to prevent an explosion as we are sensing flammable gases. It also filters out suspended particles in air, only allowing gases to go through. From the pinout diagram, we can see that besides VCC and ground pins, these sensors also come with a digital output pin to indicate the presence of a gas and an analog output pin to indicate the concentration of such gas. From the simulation, we can also see that the output voltage is proportional to the concentration of the detected gas in the sensor. MQ sensors are widely used in air quality monitoring systems, safety systems, and gas leak alarms. A disadvantage encountered on these sensors is that even though they detect the presence of harmful gases, they don't know which gas they're detecting. If the detection of a single gas, let's say carbon monoxide, is preferred, sensors such as the MQ7 can be used. Accelerometers. Accelerometers are electromechanical devices used to measure acceleration forces, which are defined by the formula acceleration equals to the change in velocity over time. To understand how they work, we can imagine a ball in a box suspended in space experiencing 0 g. If we were to move the box to the left, the ball would experience a g-force of 1 g in the x-axis. Now, if we place the ball on Earth, it experiences a g-force of 1 g in the z-axis. The forces measured by the accelerometer can be the static acceleration of the continuous force of gravity or the dynamic acceleration resulting from motion and vibrations. The change of direction of the accelerometer causes a change of capacitance between the stationary silicon plates and the suspended mass plates, which are moved by mechanical springs. This capacitance change is therefore proportional to the acceleration in the axis towards which the accelerometer is moving. Accelerometers are mainly used in physical activity devices, gaming systems, and smartphones. For example, this is how phones know when to change from portrait to landscape mode and undo an action just by shaking. The main difference between an accelerometer and a gyrosensor is that the accelerometer measures linear acceleration with respect to Earth, while a gyrosensor measures angular acceleration in one axis. The combination of both devices are used in the navigation features present in drones, cell phones, and airplanes. A challenge that these sensors present is that both are prone to errors such as noise and drift. Pulse oximeter sensors. Pulse sensors work by detecting volumetric changes in blood caused by heartbeats through any organ such as the skin. Simple heartbeat sensors consist of a light-emitting diode and a light-detecting resistor. In this image, we can see that there are two types of pulse sensors, transmission type and reflective type. The transmission type detects how much light was transmitted through the finger, while the reflective type detects how much light was reflected off the bone. The output at the detected end will be an electrical signal like the one that is shown in this image. Since blood absorbs the light passing through it, the signal pulses are proportional to the heartbeat rate. Reflection-type pulse sensors use red and infrared light, which makes it possible to also measure the blood's oxygen levels. However, it is recommended to use pulse oximeters indoors since infrared light emitted from the sun can affect the readings from the sensor. Electromyography sensor, also known as muscle sensor. The electromyography sensor works by analyzing the electrical activity of the muscle by detecting the electric potential generated by muscle cells when these are electrically activated by nerves. These sensors amplify and process the information obtained and output an analog signal that can be read by any microcontroller. The output voltage is then proportional to how hard the muscle is being flexed. This type of sensor is widely used in clinical and biomedical applications such as the identification of neuromuscular diseases and the signal control of prosthetic hands, arms, and legs. EMG sensors can have limited applications due to the adipose tissue present between the skin and muscle. EMG signals tend to be more accurate with individuals who have lower body fat. The use of this sensor is also limited by the fact that they can only measure electrical activity on superficial muscles, and many applications might also require deep muscle analysis.
Laser heat sensors. Laser sensors are an electronic devices usually used to detect the small objects. They are also used to detect the accurate positions. Laser lights have light waves of same wavelength. Due to the fact, laser lights travel in a parallel direction. It is dangerous for humans because it can cause serious eye problems if you look directly into the light when it's on. It can be used to transmit data over long distances, which is considered to be its major benefit. The light reflects at several different angles when distance changes. With the change of the angle of concentrated light, position of the image change correspondingly. I have provided 3D visuals at the different distance in the figure shown below. From three figures given below, we can easily understand the working principle of the laser sensors. The first one is laser principle at reference distance, which is also, we can say, for the close objects. And also there is shorter distance laser principle, and the third one is longer distances, as we see on the picture. Laser sensor applications. Laser sensors are used in different objects. we can use on the robot location, railroad track alignment, quality control during the concentrated block manufacturing, brake rotor thickness, welding head position, and process monitoring of the wood thicknesses. Most of the times, electronic devices are known on the basis of their applications. Laser sensors has a wide range of the real-life applications. Some of the common applications are listed in the table shown in the figures, as we said. A laser sensor, there is a good advantage and also there is a disadvantage as well. Therefore, the advantages are the parameters which can improve the efficiency of the particular device. Laser sensor advantages are the shown in the table. First one, resolve the measurement less than 1 micron at a reduced cost. Large measurements are ranges and large operation distance. For the disadvantages are for the laser sensors, like other devices, laser sensor also has a serious disadvantage. Few of the main available disadvantages are listed in the table shown figure. The first one, dust and other materials can affect its accuracy, cause serious eye damaging problems when looking direct into it. Vacuum installation can't be carried out since external cooling. As we see the video, there's an example. So for the laser, it shows for the sensor. Vibration sensors. The vibration sensors are high sensitivity, non-directional vibration sensor. When the module is stable, the circuit is turned on and the output is high. When the movement of the vibration occurs, the circuit will be briefly disconnected and the output low. At the same time, you can also adjust the sensitivity according to your own needs. Why are vibration sensors used? Vibration sensors help to detect these vibrational movements that may cause earthquakes, or more commonly mechanical failure in the machinery. Its ability to measure, monitor, and analyze such help detect the potential issues such that early preventive measures can be taken. The vibration sensor model based on the vibration sensor SW420 and the comparator LM393 is used to detect the vibrations. The threshold can adjust using an onboard potentiometer. During the no vibration, the sensor provides logic low, and when the vibration is detected, sensor provides logic high. There is three types of vibration sensor. One of them is eddy current. The second one is velocity sensor, and strain. The third one is the strain gauge sensor. The vibration sensor can be used in the wide array application, though it solidly depends on the type of vibration sensor you are using. Vibration sensor alarm, when they can use for different positions. One of them is this for alarm systems. The generating a loud beep when someone tries to break in, within the alarm stopping automatically after a few minutes. And also they use industrial health monitoring. Vibration can be used to monitor machinery health, similarly to what was talked about the earlier section. Also we can use low power wake up vibration sensor, switches, and other security systems such as car alarms. Also there's a sample here, so when we touch the table there's vibrating and the zero turns different values. Also there's IR sensors. Those are infrared sensor model is one of the most basic sensor modules that is really interesting for curious makers and dyers. An IR sensor is electronic instrument that scans IR signals in specific frequency ranges defined by standards. It then converts them on electric signals on its output pin that it's called a signal or date pin. Most common usage of infrared signals is to transmit data over the air on short distances. Almost all home electronic devices are like TVs or DVD players use infrared for their remote controls. As we see the picture, this is the IR sensor. Both senders and receiver agreed on the set of the codes so that the receiver knows what to do based on each code. The way code should be modulated as the signal is defined in different standard, and each sensor manufacturer normally tries to produce a product compatible with them so that could be used in different devices. IR sensors are available on different packages. Here you can see some typical packaging for an IR receiver, as we see the pictures. They're also available is infrared sensor modules or breakout board. Such modules normally incorporate one of the sensor mentioned above with the nice breadboard, friendly packaged together with an LED that will flash when the sensor detects the signal. By doing so, you will notice if any data is being transferred. Transmissive type IR sensors. As we see on the figure, this is a transmissive optical sensors, which is also an IR sensor. It uses pair of the components, one emitting light and the other receiving. Both lights emitter and the light detector face each other across the small gap are contained in a single module. The sensor is triggered if any object interrupts or reflects the light beam. It's also known as throw beam sensors. As you see the paper, they put it inside of the thing and it turns on. And reflective type IR sensor, it consists of the light emitter and light detector, but they are placed adjacent to each other, facing in the same general direction. When both the transmit part and receive part are mounted in one of the single module, it is known as retroactive sensor. It is triggered in one of the following two ways. An object passing in front of the light beam reflects it back to the detector. The object must be naturally reflective or must have a reflective path applied to it. A stationary reflector can be mounted opposite the light emitter, which can case detector besides, and light emitter is triggered when the object interrupts the reflector light beam. As we see on the video, there is a remote, and once it's activated with the code, it's turned on by the sensor module. And also there is a turn off button, which they coded already. There is other sensor is barometer sensors. Barometric pressure sensors equipped with the function of temperature and pressure measurement. There's common use is BMP 180 and BMP 280. These sensors exhibit lower power consumption, higher resolution, and higher sampling rate. The barometric pressure is usually used to measure barometric pressure and temperature. Besides that, we can also use the sensor measure the altitude and the relative flow height due to the fact that there is a certain relationship between altitude and barometric pressure. The sensor, how it works, as we see the pictures, contains is a diagram that formed through the one capacitive plate that is in contract with the atmosphere. Atmospheric pressure is detected through how much the diagram is deformed due to the result in the pressure. The higher the pressure, more the diagram moves, which results in a higher barometric reading. It can detect between 0 centigrade to 65 centigrade any temperature, and also there is a 0.5 meter difference in altitude. Barometric pressure sensor applications. Whether we can use these barometric pressures on cars or weather forecast predictions, able to predict the rain through the seeing if there is a rapid increase in atmospheric pressure, result in the better planning outdoor activities, maintaining health and well-being, as many believe weather correlates to human health. Also, we can use for the car engine management sensor found in the mini vehicle located in the intake manifold toward the rear of the engine. It's responsible for the pressure density measurement. This affects how the vehicle rises direct different air pressures affect engine oxygen and its fuel requirement. Also, we use for the planes as well on the same idea. We can easily get these values with measurement. These measurements are temperature measurement, pressure measurement, and altitude measurement with the same sensor model. This is the example of Arduino output. As we see, we can get the altitude, pressure, and temperature every different times. On this slide, there's a small example. The sensors, when activated, it's sending to the Arduino with these values, which is altitude, centigrade, and the other information.
A flex sensor is a type of sensor that is capable of measuring the amount of bending when stuck to an object or a surface. For example, if we were to stick a flex sensor onto a wallet, we would be able to measure how much it is bending by using that type of sensor. Flex sensors work like a variable resistor. The main part of the sensors can contain items such as conductive ink, it can contain optical fiber, capacitors, and another item called velostat, which is a pressure-sensitive conductive sheet. The way how a flex sensor works is that when it's bent, the conductive particles inside the sensor spread, increasing the resistance. Now, it may not always be conductive particles such as conductive ink or velostat, but in general, the idea is the same. Where if the particles are, if it's stretched, if it is straight, the particles will be closer together, which means less resistance. When it is bent, it is further. These particles are further apart, which means more resistance. They're commonly used to measure the angle of the item they're attached to, as I mentioned before, and they've been used in things like the Nintendo Power Glove. A color sensor is a sensor that is able to tell individual colors from each other. The way how these work, they need three different items. They need a light source to illuminate red, green, and blue. They need an object that's going to be measured, and they need a receiver that can detect the reflected wavelength. The way how these sensors work is that first the light source will shine onto the object that we want to measure. Depending on the color of what the object is, a different light will reflect from it, either a red light, a green light, or a blue light, or a mixture depending on what the color is. The receiver will pick up these wavelengths that were reflected back and then will then be able to tell what color they were through these colors. Now, if red, green, and blue are the basic three that are supported by these sensors. However, if it does end up being a mixture of colors, such as if it's the color such as yellow or something else, then yellow, for example, would be a mixture of red and green, and then, for example, white would be red, green, and blue because the mixture of all three create those colors, and then none of them would create black. So a soil moisture sensor is a sensor that works by the dielectric constant. The dielectric constant is basically just the amount of electricity the soil can transmit. In other words, you can consider it as why you're told never to put electric devices where water is, because water is conductive compared to air. If the soil moisture is high, meaning lots of water, it's easily conductive and the resistance is low as they can pass through the two probes as shown as the image on top. If the soil moisture is low, however, meaning there is little to no water, the resistance is much higher because it has to pass through pure dirt and air, meaning the resistance is higher and less voltage is going to pass through. The way how you measure it is through the resistance or the voltage. And then it's commonly used in farms to measure irrigation or to have automatic irrigation, or also just used for hobbyists as well. A rain sensor is simply a sensor that can detect rain or raindrops. There's two different types of sensors depending on which application is going to be used. One is an infrared light rain sensor that is commonly used for irrigation systems or on cars for your automatic wipers. And then another is generally used by hobbyists, which is just a printed circuit. I'll go more into detail in the next two slides. Now, the hobbyist rain sensor is a pretty simple sensor. The way how this works is that it's just simply a printed circuit, and what it has lines that can be shorted when the raindrops fall on it. When they're shorted and they're because of the raindrops, this creates less resistance because it's easier for the electricity to pass. This, which then can be measured. This is somewhat similar as to the flex sensor, as to where it's a variable resistor, to where the more water there is, the less resistance. And when the drier that the sensor is, the resistance increases because it must pass through the whole way. Now, the rain fence sensor for car is a little bit more complex. The way how this one works is by beaming an infrared light or an LED towards the windshield at a certain angle. If the windshield is dry, then what will happen is that the IR beam or the LED beam will bounce and reflect back and then be read by a receiver. And because there is no obstructions or anything, it will just bounce back perfectly and it will receive it with the same or with a little bit lower, but generally the same or high intensity. Now, if there are raindrops on there, which will affect if there are raindrops on there, what will happen is that when the light shoots out from the IR or the LED, these raindrops will differ the index of refraction, meaning it's going to bounce differently than it was if it was dry. And because the um the receiver does not account for this, it will receive less of a intensity when coming back. So if there's a lot of raindrops, it might get a really low intensity. Meanwhile, if there is just a little bit of raindrops, it might get a somewhat lower intensity. The, be, by measuring this intensity, we can tell how much rain there is, and then otherwise, how much do we need to power the windshield.
Hello, this is Alexandra, and I will be talking about biosensors. Recently, biosensors have shown immense potential for applications in tissue engineering and regenerative medicine. Biosensors are gradually becoming an integral part of tissue engineering systems, particularly in microfluidic tissue engineering models. A biosensor is any piece of hardware that interacts with a biological or physiological system to acquire a signal for either diagnostic or therapeutic purposes. Biosensors are composed of sensing elements and a transducer. The sensing element selectively recognizes a species of interest through a reaction, specific absorption, or other physical or chemical process. The transducer converts the results of this recognition into an electrical or optical signal to be measured. Biosensors that include transducers based on integrated circuits, microchips, are known as biochips. Specificity and sensitivity should be the main properties of any proposed biosensor. For engineering applications, biosensors are becoming an integral part of tissue engineering systems. For other applications, it includes pharmaceutical industries, monitoring environmental pollutants, biological warfare agents, medical diagnostics, research and development. So biosensors can be classified according to the recognition element as a bioaffinity sensor, enzyme sensor, transmembrane sensor, or a whole cell biosensor. This is also can be determined according to the transducer as electrochemical, optical, piezoelectric, and calometric sensors. The main types of transducer used in development of biosensors can be divided into 4 groups. These can be used in purified form or to be present in a microorganism or in a slice of intact tissue. The mechanism of operation of these bioreceptors involve the conversion of an analyte into a sensor detective product, detection of an analyte that acts as an enzyme inhibitor, or the evaluation of a modification enzyme properties. So for electrochemical transducers, they're described as a self-contained integrated device which can provide specific quantitative or semi-quantitative analytical information using a biological recognition element. Some challenges with these transducers is that for proper functioning, the solution membrane interface should remain ideally polarized and thus impermeable to the passage of charge. Failure to meet this will result in poor sensitivity. The second type of transducer was the optical transducers. An optical transducer can use a wide range of biological materials, from enzymes, antibodies, antigens, receptors, and NA to the whole cells and tissues. Advantages of these transducers is the ability to use safe, non-electrical remote sensing of materials. Several optical devices have been developed and successfully applied in cancer detection and metastasis, as well as arthritis, inflammatory, cardiovascular, and neurodegenerative diseases, viral infections, and drug screening. On the right is a schematic diagram of the biosensor. So it has a sensitizing layer, an antigen, and a glass substrate. Lastly, I'd like to speak about the SPR optical sensor, which comprises of an optical system, a transducing medium which interrelates the optical and biochemical domains, and an electronic system supporting the opto-electronic components of the sensor, allowing data processing. To conclude, biosensors can be an immense importance in tissue engineering applications, particularly in maintaining three-dimensional cell cultures, and monitoring these analytics can give insights to cellular activities in real time. Thank you.